Buongiorno a tutti e benvenuti a questo nuovo webinar. Gianluca, grazie.
Grazie Laura e buongiorno a tutti. Innanzitutto benvenuti e grazie per la vostra partecipazione a questo webinar che abbiamo organizzato per i nostri clienti del settore industriale. Assieme a me ci sarà il nostro Senior Application Specialist Fabrizio Ghisolfi e come spesso accade in questo tipo di presentazioni, con noi avremo un team di specialisti della PAC o Analytical Controls, azienda del gruppo PAC, che ci supporta e le quali soluzioni vengono da noi distribuite da pochi anni dopo la nostra fondazione, quindi dai primi anni del 2000, e che contiamo alla fine un numero di strumentazione installata che si avvicina oramai ai 200, alle 200 unità. Quindi avremo con noi Arian Van Zip, Theo Bouquet e Rob Strick direttamente collegati dalla sede PAC di Rotterdam. Thank you Arian, thank you Theo, thank you Rob, good morning and thanks for your participation in the webinar.
Morning.
Abbiamo scelto di svolgere questo webinar sull'argomento SIMDIS, quindi distillazione simulata, in quanto è una tecnica estremamente diffusa nei laboratori che si occupano di caratterizzazioni di combustibili. È una tecnica, dicevo, molto applicata e che poi estende appunto il suo utilizzo su prodotti che vanno dai più leggeri ai più pesanti fino ad arrivare ai greggi. È una tecnica che utilizza la gascromatografia in un modo anche un po' atipico, soprattutto quando guardiamo un'analisi cromatografica su un prodotto finito, su un prodotto finale. Non vediamo i picchi ben risolti, ma abbiamo un cromatogramma con una forma un po' diversa, ma in realtà sfrutta appieno la tecnica gascromatografica nella sua tecnica di ripartizione, quindi utilizzando la colonna come colonna di distillazione, sfruttando però migliaia di piatti teorici. Lascio ora la parola a Fabrizio Ghisolfi per una breve presentazione sul contenuto del webinar. Volevo solo ricordarvi che per qualunque domanda potete utilizzare la chat che trovate sulla piattaforma, e al termine della presentazione vedremo di darvi una risposta. Il webinar poi condotto dai colleghi di PAC sarà in lingua inglese, ma comunque un inglese molto semplice e comprensibile, come normalmente sono abituati i nostri colleghi per il nostro mercato. Do la parola a Fabrizio e ci sentiamo poi più tardi.
Buongiorno a tutti, spero mi sentiate bene. Ho avuto un piccolo crollo della rete in questo momento, ma probabilmente siete in grado di sentirmi, eventualmente confermatemi il contrario. Siamo qua a rinnovare il nostro rapporto con una tecnica e in particolar modo anche a rinnovare il rapporto con un nostro partner, un partner che possiamo definire come primo al mondo nella produzione e nella proposta di soluzioni analitiche realizzate su gascromatografia e non solo, ma per quel che riguarda SRA, la promozione di queste, e in ambito petrolchimico. In un ventennio di rapporto, anzi in più di un ventennio, con PAC abbiamo potuto proporre una gamma molto ampia di tecnologia dedicata alla simulazione, alla distillazione simulata, applicazioni che hanno più o meno raggiunto tutti gli scopi di questa tecnica, quindi dedicata alla distillazione di crude oil, di residui, di oli lubrificanti, di gruppi petrolchimici 3 e 4, quindi jet fuel, cheroseni, gasoli e diesel, nafte, perché no, sino ad arrivare al prodotto finito benzina e ai suoi intermedi di lavorazione. Perché oggigiorno parliamo ancora di distillazione simulata? Consideriamola una vecchia conoscenza del mondo della petrolchimica, considerata sicuramente la più vecchia, ma il modo più comune di separare, a partire da un greggio o da suoi sottoprodotti, vari gruppi di composti. Pensate alla gascromatografia, che in un certo senso poi ha potuto esaltare, grazie a una tecnica più moderna, una caratteristica che ha visto la distillazione come precursore, quindi l'utilizzo di differenze in punti di ebollizione. Una tecnica, abbiamo detto, comune, le cui metodiche hanno dato forza e dati utili al mondo della petrolchimica al fine di definire meglio caratteristiche del prodotto e rendimenti dello stesso. Quindi HT-SIMDIS 86 consideriamo tecniche comune e non vecchie o tali, perché è tuttora ancora in utilizzo. Di conseguenza la HT-SIMDIS 86 è caratterizzata da un piatto di distillazione, ma come la D1160 sottovuoto per prodotti più pesanti, sino ad arrivare alla TVP o la D2892 che utilizza un numero di piatti teorici compreso tra 14 e 18, se non ricordo male. La distribuzione simulata in gascromatografia parte dagli stessi presupposti, quindi esaltare la differenza in punti di ebollizione al fine di isolare, separare gruppi di composti o sino addirittura separare singoli composti. Il goal, diciamo, i vari traguardi della gascromatografia in simulazione, grazie in distillazione simulata, sono la possibilità di produrre true boiling point, quindi punti di ebollizione sempre più associati a una minor quantità di composti se non appunto al singolo composto, quindi true boiling point a ogni punto della distillazione con dati inerenti e di alta efficienza cromatografica, sviluppare una maggiore accuratezza, ripetibilità e precisione dei risultati, e nonché una forte automazione e, come potete immaginare, anche alla necessità di una minor quantità di campione, oltre che a una marcata velocità delle analisi prodotte. Distilliamo perché? Beh, lo sapete tutti voi meglio di me, comunque è un controllo di qualità del prodotto, sicuramente ci permette di essere capaci di stabilire se il prodotto è conforme alle specifiche di acquisto o eventualmente di impianto, ci permette di regolare alcuni step della produzione, di conseguenza di poter mettere mano al processo e alle sue caratteristiche, nonché ci permette di predire quelli che saranno i prodotti della torre di distillazione. PAC ha sviluppato, come vedremo poi, sicuramente detto e sviluppato da loro, distillazioni simulate per la maggior parte dei prodotti provenienti da una torre di distillazione, quindi diciamo da un greggio a un prodotto finito e anche miscelato, come la benzina finita, e così da coprire, diciamo, un intero portfolio di soluzioni di cui alcuni di voi hanno dimostrato di essere a cui essere interessati e necessitare di tecnologia per produrre determinate dati al fine di battezzare positivamente o meno il prodotto, nonché il processo con cui è stato realizzato questo prodotto. Non voglio dilungarmi troppo perché rischierei di ripetere quello che poi i colleghi stanno per esporre con dovizia di dettaglio. Lascio quindi la parola a Tio Bocche e eventualmente anche a Rob Strick per esporre una presentazione alquanto interessante.
Grazie Fabrizio, thank you. Okay, Tio.
Yes.
Now we see upstairs. You can switch the two screen. There are on the top.
On the top.
Yeah.
Screen monitor 2.
Perfect.
Yeah?
Yeah.
You see the main screen?
Yeah, we see the main screen.
Sure. Yes.
Yeah?
Okay.
Perfect.
Yeah, perfect.
Perfect. Perfect.
Thank you.
Good morning, everyone. Sorry, I have to do this in English. My Italian is not that fluent, or even non-existing, I would say. So we'll do it in English. If needed, we can always have translation from our friends Fabrizio and Gianluca. So the topic today is about why using SIMDIS. Before going into that, very briefly about and let me see how to get to the next screen. There we go. About PSE. PSE is a global company with offices all around the world, and we are provider of analytical equipment, analytical instruments for the basically oil, gas, and petrochemical industry, both laboratory and online. And our product portfolio varies from physical property testing to chromatography to flow spectroscopy, etc. And the company exists for quite a number of years already, and having a huge number of instruments installed globally. Within PSE, which is a kind of, let's call it umbrella company, we have all kinds of brands making different kind of instrumentation, like ICON doing online instrumentation, physical properties, and specifically today about chromatography from AC analytical controls. Company founded in 1981, so 40 plus years of experience in this industry. The agenda for today, I'm first gonna do an introduction on SIMDIS. What is SIMDIS? Then a few applications to highlight, and then about the market and the economical incentives, and that's basically why would you use a SIMDIS and where can you use a SIMDIS. And at the end, there is obviously time for questions and answers. So let's look to SIMDIS, what it is. First of all, distillation. We all know that if you have a pure component like water, that it boils at 100 degrees. If you have a mixture, then you talk about a boiling range. And that is where, if you want to know that boiling range, that boiling distribution, then distillation comes into place. It's a separation technology, separating a liquid mixture by their into more or less individual or fractions based on selective boiling points. And if we look to the industry that we focus on, we call that the HPI, hydrocarbon processing industry, oil and gas refineries, test laboratories, etc., then this is the main used process. And what we aim for is basically this, boiling point versus mass percent or volume percent, at least a fraction. And this is then a graphic representation where here we do it in numbers, either percentage versus boiling point or boiling point versus percentage the other way around. That is what we aim for when we do distillation in a laboratory or online. If we look into online, then SIMDIS, different ways to write SIMDIS. Basically, it is simulated distillation. People name it SIMDIS, people name it SIMDISTs, whatever. It's all about the same technology where we do a boiling point distribution, determination of that by using gascromatography. And the concept is based on the assumption that components elute from a column, a GC column, on their boiling point order. That's one of the basic fundamentals of chromatography, where you can separate on boiling point is one of the ways of using chromatography. To get SIMDIS data, you need to introduce the sample, of course, in the GC, and we use a specific detector for that, more about it later. Then a separation on a column, a detection using a flame ionization detector, and then you need to get a relation between retention time and temperature. That's in the next slide. And from that data, you get the boiling point distribution. That relationship between retention time and boiling point is shown over here in this graph, where you look, let's say this is a chromatogram from a sample introduced on a SIMDIS. So this is the total sample, where you say if you take the area and you take certain percentages of the area, let's say this here in the middle is 50%, this might be 40, 30, etc. That relates to a retention time, but we don't want a retention time, we want boiling point. So if we relate that to a mixture with normal paraffins in this case, where we know the boiling points, like here for C10, C14, C20 as example, we know when they elute. Then you can change your time axis into a boiling point axis. That's graphically represented here, and then you can change your percentage to retention time into percentage to boiling point. That's the whole thing you want to do in distillation, as I've shown in the earlier slides. And as an example here, a typical SIMDIS report of a diesel with some fame in there even. So what you see is your sample and then the retention time, but that retention time is related to the boiling point, and from there you get your percentage versus boiling point. This is the whole concept of SIMDIS, introducing a sample on the GC column where it elutes in boiling point order, and you get the area of that fraction and take percentages of that total area and relate it to retention time, and from retention time to boiling point, resulting in a report like this. This is a typical example, like a diesel with a fame with biocomponent in there, but there are many other types of SIMDIS, types of products you can analyze on a SIMDIS. And what you see here is let's say a few examples where it varies from gasoline up to crude oil, but some intermediate fractions like the distillate, the vacuum distillate, or even the residue from a vacuum distillation tower or from a atmospheric distillation tower. There's very heavy products, which I'm going to talk about later on, but even diesel, gasoline, you name it, all kind of products, all analyzed on a SIMDIS based on the same concept. If you look to tenderization, then there are many methods describing the simulated distillation technology. You can group them into low, medium, high, or whatever grouping you want to do. You see here the methods, the maximum carbon number, the type of products, and the boiling range for that specific product or that method. And within the PAC, the AC Analytical Control SIMDIS portfolio, we cover all these methods. And we have SIMDISs according ASTM 657, or 22887, whatever. All kind of methods, but all at the end based on the same concept as described before. And basically the difference is the type of columns used to get the separation of these components. For what we call high temperature SIMDIS, which is typically used for heavier products, I'll come to that, and low temperature SIMDIS for lighter products like gasoline or jet fuel and so. Same principle, the only difference is the thickness of the stationary phase. And you can imagine with chromatography background that heavy components, if you introduce them on a thick stationary phase, that it will take a long time for them to come out, if not too long or if not at all. So therefore, for high temperature SIMDIS, we use a thin stationary phase, and for low temperature SIMDIS, we use a thick stationary phase. That is the difference between all the methods and, of course, the oven temperature programming. Looking at typical columns for that, you see here typical examples of the film thickness for high temperature SIMDIS relative short column with a very thin stationary phase. And for low temperature in the gasoline range, a longer column with a very thick stationary phase, and the mid-range is in between. To do SIMDIS, what do you need for that? Well, basically three things. Hardware, being a GC with an autosampler for the sample introduction. The GC is configured with a specific inlet to introduce the sample in such a way that there is no discrimination for light and heavy components, that residual components like asphaltenes stay in there, that it can be used for solvents like carbon disulfide, which is typically used in high-temp SIMDIS, etc. And we use, PSC uses for a long time already the TPI, the temperature programmable inlet. That is around for decades already. Second thing is the non-polar boiling point column, which separates on boiling point, obviously, and then an FID, which is a mass selective detector detecting what comes out of the column. Second thing you need is software to process the data coming out of the system. And first of all, you need a chromatography data system that can, for example, be Agilent Open Lab or Agilent Chem Station. And in addition, some dedicated software, SIMDIS, to calculate the boiling point distribution and a whole lot of other parameters from that and report it as we have seen in earlier slides. And here you see, for example, a screenshot from our SIMDIS software based on our Iris software platform, which we use for all the PSC applications. In addition to that, you also need to calibrate and to verify the instruments. And for that, you need calibration and reference material. You obviously need a standard boiling point standard, normal paraffins, for which we know the boiling points. Then we need a reference standard to check the performance of the system, and some quality control samples as an additional check. And the typical thing for PSC, AC analytical controls, and that's what we are doing for decades, we deliver the whole system as a total package, including the hardware, including the software, including the calibration and reference material, as an analyzer which has been tested in our factory with the calibration and the reference material. And we deliver it to you as a customer as a guaranteed turnkey solution. Very briefly about the software. It is what we call work-oriented and workflow optimized software, where basically everything from the moment of sample introduction, which you introduce into your chromatography data system, you start your analysis, and everything afterwards can be done automatically, from importing it in our software, from calculating the results in all different kind of ways, from generating a report either as a PDF or a CSV file or whatever, and even export the results to LIMS. That can all be done automatically. If you prefer, you can do these steps manually as well, partly of it or everything manual or everything automatically. We offer our software as standalone configuration, so a computer next to the GC or in a client-server environment where all your data and your methods is stored on the server, where you have clients from where you start your sample analysis, from where you process your data, etc. So standalone or a client-server configuration. So far then about what is SIMDIS. Let's look into a bit more detail about the applications. There are many applications, many ways where and how and why you should use SIMDIS. I'm highlighting 5 of them over here, which is the AC861234, which is SIMDIS not only reporting the carbon distribution, but also the sulfur and the nitrogen distribution. For example, high temperature SIMDIS for residual products like atmospheric and vacuum bottom. For also high temperature SIMDIS for biofeedstocks and waste plastic pyrolysis oil and all kind of other type of, let's say, bio and petrochemical type of applications. And crude oil SIMDIS. Now, these are just a few examples. We only have, let's say, 1 hour today, so I'm gonna talk about these 3 highlighted here: AC861234, high temperature SIMDIS for residual products, and high temperature SIMDIS for bioproducts and pyrolysis oil. So let's look at AC8612 and AC8634. The AC8612 is, well, to be honest, it's not a SIMDIS. It is a dedicated application in our DHA, Detailed Hydrocarbon Analyzer software, where we calculate the boiling point distribution, and that's why I included in this presentation. So the boiling point distribution of a product based on the results from a DHA analysis, and then a calculation afterwards based on the fugassity film model and all kind of other parameters of the individual components, all kind of calculations using the individual component characteristics, some thermodynamics, and it mimics, it simulates what is going on in a physical distillation, where you have a flask with 100 ml of sample, which you bring to its boiling point. It starts to evaporate it. It condenses near the thermometer, and you collect your fractions in a metering flask, as you see, for example, here. So that is what we do with the 8612. We calculate the boiling point distribution similar to physical distillation based on individual component characteristics and some thermodynamics. And it will give you the all the requirements from the physical distillation methods, like time to initial boiling point, the start temperature of the sample, the distillation rate, etc. And we report all similar things: IBP, distillation points, either evaporated or recovered, the loss, the recovery, and so on. A good thing to mention is that there is no standardization method describing this application. It may be a matter of time, but for now it is not. So to summarize, what you do is GC analysis to separate individual components, identify and quantify the individual components. From that, together with the physical properties and the model, we calculate the boiling point distribution according to D86 or the European equivalent, the 3405 for group 1 and 2 type of products, so gasoline, naphtha type of products. From that, you get the boiling point distribution, as you see here for group 1 and 2, boiling point versus volume percent, or the other way around, of course. You can have certain cut points. You can report evaporated or recovered data, all in volume percent, of course. It reports the loss, the recovery, the residue, the read vapor pressure, time to recover, the 5 mil, etc., etc., all as requested by the D86 method. There's a comparison to the D86. Here are some results from the 8612 and the D86 data. And what you see, and it's in this graph, the light blue is from the AC8612 and the dark blue is from the D86 itself. And as you can see, there is hardly any difference. Same for this kind of product, even for a gasoline with ETB. You see there's a perfect match for the data. The other application, 8634, is different. It correlates SIMDIS data, mid-distillate SIMDIS data, into the D86 or ISO 3405 methods. So it's correlating SIMDIS data, where the 8612 calculates data for the composition. And the AC8634 is, well, you can already guess that it's for group 3 and 4 type of product, like the jet fuel and the diesel, and it is based on a correlation as described in the HTM 2887 methods and also in the ISO methods. And there is an older correlation which was called STP 577, which was updated years ago into this new correlation that we now use in our SIMDIS software. And what you get from that is, well, I would say exactly the same chromatogram from SIMDIS and the 86 data based on the correlation with the volume percent versus boiling point, also some cut points. What we do not report here is time to IBP, the residue, the loss, etc. To compare the data, similar graph as on the 8612, here you see two graphs, one for the diesel and one for the jet fuel, where the dark blue is SIMDIS data and the light blue and the orange are D86 data, where orange is the real D86 and the light blue is from the correlation. And you can see here for both jet and diesel, we have a similar perfect correlation as the AC8612. And you can see here the difference might be small numbers, but in general, it's specifically in the middle, it's less than 1 degree or max 2 degrees. If you look to the jet fuel, you see that it's a very narrow. So a very good comparison between the methods. So to summarize these two applications, they are an alternative for the D86 or the ISO 3405 analysis. And the nice thing about it is that you can automate this on a GC, obviously. So you can run a sequence, you can run multiple samples in a sequence after each other, and roughly 4 to 5 samples per hour unattended, versus on the physical distillation, where you continuously have to change your flask and your sample, etc. The AC8634 is for the jet fuel and the diesel spec listed as an alternative method. So if you look to the jet and the diesel spec, you will see that it's saying that the correlation data can be used to certify products like a jet and a diesel. Another nice thing about it is that these two applications can nowadays be combined in one GC, one channel for the 8612 and one channel for the 8634, which obviously gives you a very high sample throughput, far more than what you will get with with physical distillation, and all automated, obviously. In addition, health and safety plays a role over here, because you have less vapor emission and so on. There's less or no risk for fires and so on. And the overall cost per analysis will be lower, as a summarize on the 8612, 8634. Let's go to the next application, high temperature SIMDIS for residual products. You can use high temp SIMDIS for many different products, varying from crude to FCC, feed, etc., etc. For the coming slides, I would like to focus on residual products and explain a bit more about that. But when we talk about high temp SIMDIS or high temperature SIMDIS, what are we talking about? Well, it covers the analysis, the simulated destination analysis of products with a final boiling point relatively high, and we typically say it's beyond C60, 620 degrees. Just a definition, but this is roughly where we say from there on we call it high temp SIMDIS. And you can report up to C120, 750 degrees, depending on the methods you use. It can be that your sample may have products, may have components with a boiling point even higher than the C120 or the C100. And that would mean that we talk about residual samples, and I'm going to explain about that in the coming slides. But the concept is that you only report up to the last point of calibration. For this type of products, you obviously need a column with a thin film, with a thin stationary phase, because you want these heavy components to elute as well. And you need to program the oven to a relative high temperature. We go up to 430 degrees C. Because of this thin film and in most cases the nature of the products that you analyze, samples need to be diluted. Because of viscosity, sometimes samples are even solid at room temperature. So you need to dilute them to be able to bring them in the inlet and the column. Because of the thin film, you don't want too much product going in there, so you need to dilute to avoid column overloading. And overall, it's for common practice, carbon disulfide is the best solvent to use. It's a good solvent. It has hardly any response on the FID and so on. I'm not going to go in more detail on that. I'm more focusing on the end, on the residual part in this presentation. And then finally, important to mention that it should have the product you analyze should have a significant boiling range. So more than 50 or more than 100 degrees. And light products like naphtha or gasoline or diesel are typically not analyzed on a high temperature SIMDIS. If we go to the challenges that you may face in high temp, and then specifically for residual fuels, for residual products, there are a few methods describing this. ASTM 7169, the EN 15199-2, and the IP 507 are all for products, materials having a boiling point beyond 700 or 750 degrees C. And here at the bottom, you see a typical example of that. This is a residue from a vacuum distillation tower. We're not going to look into the beginning. We'll look at the end for this moment. And you see here that at the end of the analysis, which is highlighted here by this dotted line, that still sample may come out, although it comes back to the baseline quite quickly. So we have challenges with the final boiling point and the recovery. What are the challenges with the final boiling point? Well, we have said in the beginning that SIMDIS is based on taking the total area and then distribute that over its boiling points, over the percentages. But by definition, then you will have a start and an end. But as you have seen in the previous slide, there is no end. There is still sample eluting at the end of the analysis, although not much, but there's still something coming out. That means that you will have not 100%. And by definition, the final boiling point is set as equal to 99.5%. So if you do not have 100, you very typically will not have 99.5% as well. So you can not report a final boiling point. That is the conclusion you draw from this graph and the previous graph. So if you have still sample eluting at the end, you cannot report a final boiling point because you do not have 100% of area, and thus not 99.5. So you need to figure out, at least if you want to, what is the recovery, how much of the sample introduced is coming out. And there are two ways of doing that, but if you read the methods, they say you have to take the total area, and at a certain moment when your signal at the end is not changing anymore, we define that as the endpoints. And here you see two graphs. This might be a bit small, but you can clearly see here at the end, there is no sample eluting anymore, so you will have an endpoint, while at this one there is no endpoint. So what you typically do is for this type of product, you take the total area and distribute it over 100%, where in this case, where you have no endpoint, thus not 100%, you calculate it over the found recovery, and I'll come to that in the next slides, and you call that a residual sample, while this is a fully eluting sample. To say whether you have 100% is easy. You see an end and then you start and you take the total area. But if it's not, you need to have a clear definition of the area, and you do that by simply taking every measuring point, every area slice from your chromatogram as you've set it in your chromatography data system. In this example, we have 100 heads sampling rate of the signal, and that means that every 0.02 minutes there is a area slice as described here in this slide. I will not go into much detail. And then you subtract the blank from it and you get a corrected area slice, and you all add them up, and that gives you an area. And you compare that area to the area of a reference sample, which is eluted for 100%. And that is what these two methods describe. Basically, it is the recovery calculation is an external standard calculation where you compare the area of your sample with the area of a fully eluting sample, and you get a certain percentage of recovery, and then you distribute your sample over that found recovery. All pretty theoretical, but at the end, it's about finding the boiling point distribution for the fraction that has eluted from the column based on the found recovery and the calculated recovery, as you see on this slide. A role in that plays the sample introduction that I mentioned, external standards. So it needs to be an accurate sample introduction. And we program the inlet, we program the oven up to 430 degrees C. So the area around the inlet, where basically you're sampling your autosampler, where you're sampling the autosampler is located, can get pretty warm. And to overcome issues with sample and solvent evaporation, which might happen because of that, we use a trick in the autosampler, and we call it the optimized for light solvent autosampler, where we blow cool air around the inlet area, around the sample, keeping the sample below the boiling point of the solvent, as you can see here, where we had a number where we measured the temperature in a standard system without the light solvent optimized autosampler versus one with where it stays nicely below the boiling point of carbon disulfide. Yeah, well, how important is that? Well, the importance is shown over here, where we have set a number of analyses without the light solvent optimized sample, and you see that the total area, the RSD of that, is around 7%, and that affects the recovery, of course, because you look at the external standards area of the sample. Whereas with the light solvent optimized, where you avoid evaporation of carbon dioxide of the solvent, you have a much better relative standard deviation. Some other challenges around it, and in general, you obviously need a good blank, and these are pictures from the methods. You need good clean carbon disulfide, you need the light solvent optimized autosampler, you need to make sure that your system is well conditioned so that your sample comes nicely back to the baseline. Inside the inlet of the TPI, your residue, your asphaltenes may accumulate, as you can see over here, so you need to replace that frequently. The good thing is that it accumulates in the liner and not in the column, so it's not affecting your separation in the beginning. And that's one of the very nice features of the TPI. You obviously need to do accurate dilution of the sample because you do external standards. You need to make sure the system is calibrated properly with a good boiling point calibration, and the reference oil, which we use as 100% sample as the calibration standard for the recovery calculation. And obviously you need to have a clean system with solvent and waste files cleaned properly, etc. So that is about high temperature SIMDIS of residual fuels. Challenging, but very much doable, used a lot. Take care of these challenges as listed over here. Make sure you use an optimized autosampler to avoid the evaporation so that you get an accurate recovery. Make sure that you do a proper calibration so that you get an accurate recovery. And then the software will take care about a good calculation of the distribution over the found recovery of your system, no matter what type of product you have introduced. Then, as a third application, also based on high temperature SIMDIS, but in a, let's say, a relative new market, a relative new area. And that is around biofuel feedstocks and petrochemical products like waste plastic pyrolysis oil. And that is where high temperature SIMDIS can play a role as well, because looking into the biofuel feedstocks, and I'll come to that later in the presentation, well, there's a large variety of products from frying oil to, well, you name it. And the product quality can change, can vary a lot, if you can even talk about quality. There's not so much standardization around the topic yet, and it's still a growing industry. It's an industry in development, the biofuel. We're used to using bio components into gasoline and diesel, but not so much into this new type of feedstocks. Just a few examples of products analyzed on a high temperature SIMDIS, different feedstocks like this fatty acid products. And this may not be the best chromatogram you can think about when you talk about high temp SIMDIS, but it definitely gives you an indication of the type of product. Is there a heavy tail in the end? Is there a big fraction of light components, etc., etc.? The boiling point distribution itself may not be 100% accurate, but it's definitely something for trend recording and indication about the product quality. Something similar here on used cooking oil contaminated with a bunker oil, you see complete different chromatogram, light fraction at the end, some residue even at the end. And here, fatty acids. Now I should have shown this one before. So this is the standard fatty acids. You see nothing here, and if I go to this one, you can see it's contaminated with, in this case, a tocopherol product. You see there's product over here. And again, you get the boiling point distribution as represented here by the red line. Completely different than what we are used to with SIMDIS on products like diesel, jet fuel, crude oil, etc. But it gives you the information you may need. So it gives you a fingerprint of the chromatogram. It gives you an indication of the product composition. Is there heavy product contamination? Is there light contamination? Whatever, you can build your own, let's say, database of good products and contaminated products, all kind of ways to use high-temp SIMDIS, and typically as a fingerprint. To mention, these products do not fit in the scope of the standard SIMDIS methods. I already mentioned that. But again, it gives you a good indication of the boiling point distribution, although it may not be 100% accurate. And in addition, components which you may find in the used cooking oil, in the FAME and so on, maybe residuals, maybe acids, maybe polar components, oxygenated kind of components, etc. They typically stay in the inlet, and therefore, and sometimes even a bit in the column. So therefore, you may need to do more conditioning than what you might be used to in standard high temperature SIMDIS. So biofuel feedstocks can be done on high temp SIMDIS with some remarks as listed over here. Completely different topic is the waste plastic pyrolysis oil. It's a oil which can vary a lot. It can be, depends on the source used to make it, and so on. There can be significant amount of lights, it can be a significant amount of heavy, and so on. So this is really a, let's say, weird product. Also, that may not be the right word to use, but doing a boiling point analysis on it gives you, on the other hand, a good insight in what it can be used for. How much light is there? How much heavy is there, etc. And in addition, it shows you, and we'll see two examples in the next slide, whether it's a paraffinic product, yes or no, which may result in the use of it for something different than, depending on what you had in mind. Two examples over here. Sample one, this one, which is a heavy product. There is residue, there's a lot of light, it's paraffinic. You can see the normal paraffin sticking out here. And from that, you get your boiling point distribution with the red line and the percentage versus the boiling point. This is another waste plastic pyrolysis oil. Less light, less paraffinic, contains non-solvable particles with a different recovery and again here the results. So just two different examples. We've seen a couple of examples on how SIMDIS can be used, other than the regular thing like a refinery process control, like crude oil evaluation, etc., etc. But we've taken these three as an example to what can be done with SIMDIS, why using SIMDIS. And if we go to the market and the economical incentives, you could say, well, SIMDIS can be used for different purposes. It can be used in the exploration part, so the crude oil evaluation. And for that, you can use high-temp SIMDIS, you could use the crude oil, you can use the CNS SIMDIS, also kind of SIMDIS applications for crude oil. If we look to the refining, the processing part of it, you can use it, of course, for process control and process optimization. And these are the methods focused here on the ASTM methods, but the European and ISO equivalents are there, of course. It can we come to that later. And the product specification. I mentioned that the mid-distillate correlation, the HT-SIMDIS, can be used to certify products, jet and diesel. This is the, let's say, the more traditional part of SIMDIS, whereas nowadays, also for petrochemical, you can use it for the process and feedstock control. You can use it for the naphtha with the 8612, but you can use it for the waste plastic pyrolysis oil using the high temperature SIMDIS, and so on. There are multiple examples for that. And finally, for the biofuels with the sustainable aviation fuel and the feedstock control for the bioprocesses, mid-distillate high temperature SIMDIS, all places where we can use SIMDIS. We're gonna spend a few slides per topic on giving a bit more background information. Let's start with the exploration part, the crude oil. It's obvious that understanding the composition, the boiling point distribution of a crude, that it can tell you something about how much diesel can I get out of it, how much naphtha can I get out of it, how much heavier fractions will there be. So that is of great importance and understanding the value of a crude before you introduce it into a refinery. And here are just some examples. A very heavy kind of crude, the alba, where you have a significant fraction of resids and loops and mid-distillates and relatively light on naphtha, whereas the 40s is light on naphtha and far less resids. By doing a high temperature SIMDIS, you get this kind of information. So we know that in most, if not all refineries, the crude distillation is the first step in the overall process, where your sample is separated, the crude is separated into the different fractions. And if you know what goes in on a crude oil, you can tune, you can play with your process to get biggest amount of fractions with the highest value. And SIMDIS, high temp SIMDIS, can help you in predicting that. Looking at the refinery process, this is a typical refinery. Of course, no refinery is the same. Some may have cracking, some may not, and so on and so on. But first step, crude oil going in the atmospheric distillation, sometimes vacuum distillation, etc., and all the processes with the products coming out, where a green dot represents where distillation information can be used, where SIMDIS comes into place. And going back to that distillation tower, the optimization of the different cut points in the tower is obviously related to the price of the various products for a mid-distillated kerosene or a naphtha or whatsoever. Some products have a higher value where you want to extend your recovery from that fraction to get most out of it, of course. And by knowing upfront the information on this, SIMDIS can help you. If we go to the markets, so the trading and of the various products like the gasoline, the jet, and the diesel, there are obviously specifications for that. For Europe, when we talk about the gasoline, we talked about the EN 228. For the jet fuel, typically the DEF standard comes into place, and for diesel, the EN 590. Having the referee methods, which is physical distillation, but for the jet and the diesel, as already mentioned, the correlated data from the SIMDIS can be used. It's listed in the fuel specs that these methods can be used. And then there is even another PSC product complying to this method, which is the OptiPMD, which is also listed as an alternative. Focus here was around the jet fuel and the diesel, where with the 80-34, you will get the correlated data according to the methods to be used for the fuel specification. If we look to standardization, it's a method typically gives you a repeatability and a reproducibility that the system should comply with. And everyone can say, yeah, we comply with the method, etc. But what we as PSC, AC Analytical Controls, have done many years ago already, we have organized a performance monitoring program, a kind of interlaboratory study where we analyzed 60 plus samples, where we send around 60 plus samples to customers like yourself, where you've analyzed the data on a SIMDIS, returned it, and from that bunch of data, we get a repeatability. You see here in blue, and here graphically in blue, which is for all points better than the method, what the method is asking. So the installed base of AC SIMDISs around the world is producing data with a better repeatability, with a better reproducibility than what the method is asking for. And this is obviously a money maker because it allows you to use the data and to get tighter control of your product specifications, that get a tighter control of the 90 and 95% points and have less product giveaway and thereby a higher return of investment on this, analyzing this product. As the next one, we move to the petrochemical. I mentioned about the waste plastic pyrolysis oil. That of course has all to do with the amount of waste, with the amount of plastic waste that is floating around the world, literally floating in the oceans or at places like shown over here, with a lot of plastic, 10 billion tons of plastics. And what obviously the market is looking for to reduce this, the political situation is that we want to get rid of this waste and so on. And one way of doing that is to process the plastics and produce products which can be used for something else. And here comes the waste plastic pyrolysis oil in the picture, where plastics are cracked under low atmosphere, and you get a oil which can be used as a feed for either a steam cracker for the ethylene or propylene production, or even feed it in the refinery process and so on. For that, you obviously need to know some characteristics of the waste plastic pyrolysis oil. And one of them is the boiling point distribution, as we have seen before, the few examples that we have done on that for a specific customer. Boiling point distribution is one, but also analysis of group types or physical properties, etc., is something PSC can offer. If you look to the pyrolysis oil, it benefits, of course, for leading to a cleaner environment, to reduce the fossil fuel demand, to have a sustainable process, and so on and so on. And SIMDIS can play a role there by analyzing the products, the pyrolysis oil, and giving an indication of the yield for the various products that one can get out of that pyrolysis oil. And in addition, it shows the paraffinic nature, which can be used as valuable information as well. That about the petrochem. If we go to the biofuel, 30 years ago, 40 years ago, nobody talked about bioproducts. And over time, we have seen that bioproducts got a bigger role in our industry. We saw the oxygenates getting blended into the gasoline. We saw the FAME get blended into the diesel and so on. And the European Commission has put a statement here that from the renewables, 42%, or from the feed used, 42% should have a renewable background. And that can be all kind of things. That can be from the cooking oil, that can be from let's say the use of sustainable aviation fuel, that can be of vegetable oil, that can be all kind of products. Just a few examples listed over here. And at the end, when these products or the processed products are blended into the final products, you of course have your final product specification, like for the jet fuel and for the diesel and so on, and the gasoline. But when we talk about the feedstocks, mentioned that the quality of the products may vary a lot. As you can see here as an example, this is from a frying pan, and this is another type of more waxy components probably. Well, analyzing the quality of the feedstock is important, of course, and this is a new industry where companies, just an example here, oil recoveries, but that just for the picture, comes and collects all kind of products. And for the processing, one wants to know what is in that truck, what is in that tank, what are we going to process, and what is the value of it, and what can we expect from the final process and the products getting out of it. Is there any contamination, etc.? Everything where SIMDIS can play a role by analyzing those products, as we have seen before in a few slides. Well, that brings me to the end, more or less, with the conclusion. Why using SIMDIS? There can be many reasons for it. Product specification, process optimization, tax regulation, biofuel contamination, process control, lubricants, you name it, all kind of reasons to use SIMDIS, or where SIMDIS can play a role in add value to the product in the overall processing and the use of the products. And finally, two more slides. When we talk about PAC, we have the comprehensive distillation portfolio from gasoline up to crude oil, with the extensive scope, not only simulated, but also physical distillations. Systems have set a standard, like the crude oil, for example, was based initially and developed based on PAC products. We have a huge installed base. We play a role in standardization. And of course, we have the huge application knowledge, which we use in supporting our customers. And at the end, like listed here, we have the whole range of distillation portfolio, and whatever need, whatever requirement you have, we always do the best to offer you the best solution for simulated distillation. Brings me to the end. This is the end. A lot of information, maybe a lot of details, but it was there to highlight the options, what can be done with SIMDIS. And I'm sure there will be some questions, and feel free to answer them, put them in the chat, and we can do that in Italian, do it in English, up to you.
Thank you, Theo. Really very exhaustive presentation. Very exhaustive presentation. Penso appunto abbiamo tutti apprezzato la bella presentazione di Theo, quindi un po' dalla teoria della distillazione simulata, appunto via gascromatografica, fino poi a tutte le applicazioni e anche al coinvolgimento dei prodotti nuovi di origine bio e non solo, che si possono appunto misurare quali dati si hanno con questa tecnica. Ecco, vediamo se c'è qualche domanda. Ecco, vi ricordo c'è disponibile la chat su quale potete scrivere le domande, le curiosità. Abbiamo un'opportunità oggi importante, con degli specialisti appunto tutti a disposizione. In the meantime, Theo, a question about carrier gas, helium for sure, but there are also other carrier gases that can be used.
Yeah.
This is one
Typically,
question, and sorry, the second question, it's about the cryo. We know some methods describe the cryo, so when are necessary, when not, a little bit of clarification.
Yeah, okay.
Thank you.
Question 1, carrier gases.
Yes.
Typically, traditional helium is the gas to be used. What we see is, of course, and everybody knows that helium prices go up. It may be a challenge to get it nowadays, and so on and so on. So looking into alternatives, nitrogen, hydrogen might be optional carrier gases, and some of the methods are listing those as a gas, as optional carrier gas. If you want that can be done. We offer that option. Might be that the method is asking for a kind of minor bias correction on the results based on that. So the answer, yes, it's doable to use other gases. Take a careful look at the method and how important is method compliancy. You can imagine that for the biofeed products, there is no reason at all, and for the residual samples, etc., because that's typically a process stream and not a final product. And so standardization does not play a big role in those products. Look at the methods. Do you need to comply? Check what is in there and switch to the other gas, and we can support you by that. Yes. The second question was around the cryogenic.
Yes.
Yes.
Yeah, cryogenic is typically explained in high temperature SIMDIS methods when you have a significant amount of light products. I did not talk about it in this presentation. I mean, there's so much to talk about SIMDIS, we could easily fill a day. But I emphasized on the heavy ends. When you have a significant amount of light fraction, like in the crude oil, the method says you can use cryogenic, but as an alternative for crude oil, I would rather recommend the use of the DHA front end, which is in analyzing the light fraction of the crude oil in more detail, far more better than SIMDIS can do, and far more better than SIMDIS with cryo can do. Again, this is a matter of what does the method say? Do you have to comply to the method? Yes, no.
Okay.
Cryo is every PSC SIMDIS is, or every high temperature PSC SIMDIS is equipped with a cryo valve.
Okay, by default.
By default, liquid nitrogen. Should you want to use the liquid CO2, that can be done as well.
Posso aggiungere una cosa, Gianluca, relativamente all'opzione cryo per il forno. È prevista, allora, la 2887, l'STM di 2887 è comunque l'applicazione che è stata richiesta sul mercato e raccoglie più o meno la metà degli analizzatori che SRA e POC hanno proposto e venduto sul mercato italiano. Prevede due metodiche, una metodica A e una procedura A e una procedura B. La procedura A necessita, è mandatorio l'utilizzo dell'opzione cryo per il forno. Però, come diceva Teo, nella procedura B, quindi nella versione accelerata che noi proponiamo, la valvola cryo per azoto è inclusa di default, in modo che il cliente possa eventualmente switchare da una procedura all'altra se per caso gli è richiesto dal sistema di qualità o dall'impianto come verifica.
Ok, va bene. Vogliamo dire due parole sulla sample preparation. So Theo, about samples, I know in some methods it is possible to inject net sample, so without any preparation on other type of samples and methods. We need to dilute, to weight. Quindi chiedo qualcosa sulla preparazione del campione, perché in alcuni metodi è prevista l'iniezione tal quale, in altri c'è un minimo di preparazione. Nothing is changed, so
Nothing changed, Gianluca.
Okay.
It's the combination of the type of SIMDIS products and the nature of the product analyzed. If you think about jet fuel, diesel, they are not that viscous. They easily go in a syringe, and you use a SIMDIS with a relative thick column, so you can do direct injection there. When you go to high temperature SIMDIS, as I've shown, when you have viscous samples or even solid samples, or like, for example, like crude oil, that in combination with the very thin column, thin film in stationary phase, you need to dilute. And that needs to be accurate if you want to do a recovery calculation, as I've shown, because then you go into external standards calculation, where you need to accurately dilute your reference oil to get the response factor, and you need to accurately dilute your sample.
Okay, thank you, Theo. I have a nice question from the attendee regarding biocrude from pyrolysis. So, biocrude from pyrolysis, liquefaction of biogenic feedstock resulting in oxygenated products, so oxygen content up to 20-35%. Which cautions should be taken in assessing results, and what kind of setup shall we, as a client of an analytical HT-SIMDIS, to be sure that the analysis is not biased or affected by large errors? So we talk about biogenic feedstock, and with a high concentration of oxygenated, to 20-35%.
That's a big amount. Yeah,
that's a lot. First of all, we have to realize that this product does not fit in the standard scope of SIMDIS. Yeah, standard scope of SIMDIS is based on a hydrocarbon mixture, jet fuel, diesel, whatever type of product, with a certain boiling point distribution, and based on the nature of the product, it elutes in boiling point order from the column. We are stretching the use of SIMDIS for these kind of products. So what you will get is a good indication, as I mentioned, a good indication on the boiling point distribution. Will it be 100% correct? Probably not. Are there any other techniques for these kind of heavy products to get a boiling point distribution? Probably not. So it's the best option available. You will get a good indication. It will give you the information whether it's light, whether it's heavy, and so on and so on. And in addition, on the recommendation what to do, etc., what we could offer as PAC, and we do this more often, is analyze such a sample on the SIMDIS in our demonstration lab here in Rotterdam, and then based on that, come with recommendations on what might be the best, or what is the value of the results, or how to interpret the results. And then when we have done the analysis, we share that results with you, and we discuss about that. If you're already a user of a PAC SIMDIS, then we could do it the other way around. We could set up a call, which, for example, the two of you and Rob, my colleague here in the call, and that we say, show us the results and let us have a talk about that, so that we can advise you on how to continue, rather than just making general statements right now. We take this consultative role very serious. For us, it's not only about the instrument, but about how to use it, the value of the results, etc. So we take that role. So if needed, if interest, then we can do that.
Ok, so thank you Teo. Quindi diciamo che per applicazioni particolari PSI e noi ovviamente siamo disponibili per approfondire appunto l'applicazione. È sicuramente di interesse non solo nostro ma anche di PAC quali produttori e sviluppatori di applicazioni. Come diceva appunto Teo, non è sicuramente l'applicazione adatta, ma diciamo, è sicuramente la più,
È in grado di dare
più
dei riferimenti abbastanza
esatto, più
validi.
attendibile. Esatto, esatto. Però insomma, ho capito che con questo tipo appunto di campioni eterogenei ci possono essere magari degli accorgimenti che devono essere studiati ad
O
hoc.
sviluppi futuri, sì, certo.
Niente, abbiamo diverse domande, vediamo se abbiamo tempo, riusciamo. Teo, c'è una domanda diciamo, sul tipo di iniettore. Diciamo che per la distillazione simulata la cosa fondamentale è evitare la discriminazione del prodotto una volta che viene introdotto in colonna, quindi l'iniettore deve essere assolutamente del tipo non ad introduzione diretta e non splitter. È contemplato l'on column. PAC utilizza un iniettore a temperatura programmabile che si chiama appunto TPI, che è poi in realtà un on column a temperatura programmabile dove il campione viene deposto in un liner ad una temperatura, se ricordo bene, attorno ai 100 gradi e poi in programmata la temperatura dell'iniettore segue quella del forno con diciamo con un delta di 10-15 gradi superiori a quella del forno. In questo modo il campione viene appunto, diciamo l'iniettore e la colonna dei liner sono collegati tra loro in modo fermo, in modo sigillato e quindi in realtà è un'introduzione online, ma il campione essendo deposto nel liner è possibile cambiare il liner e quindi non andiamo diciamo, a deturpare la colonna, a danneggiare la colonna, non dobbiamo intervenire sulla colonna per una sua manutenzione e quindi riusciamo a preservare la colonna più a lungo. There's another question about the carrier gas, Theo, especially about the the hydrogen and especially in the ISO 3924 using hydrogen and converting in ISO 3405. There are some correction for the bias. You did any study, any correlation for this?
Well, that is in standardization topic of discussion. And also internally, there are in the methods is only listed a few cut points, a few percentages describing that bias correction, and less percentages than needed to report. And there is currently a discussion and a further testing going on to cover all the points as listed, so that would allow us then to include this and report all the points with the biocorrection. So there is a small bias correction statistically, whether in practice, I don't know, it's based on data. But the points listed is not enough to fully cover the correlation. So that's a bit of challenge within standardization, currently in progress.
Okay.
I hope that makes sense. It's a bit
Okay.
weird situation, but yeah.
Sure.
Okay. I have a question. Theo, the HT-SIMDIS is alternative to the ISO 3405 for the
Group
gasoline distillation is
Group
correct?
one. Group 1
It's
and
group
2.
1.
Group
Okay.
1 and 2. Yeah, naphtha, gasoline type of products.
Okay, so
All kind of, let's say, gasoline intermediate streams.
okay, so for this kind of product, yeah.
Yeah, I think the name is pretty descriptive. AC stands for AC, 86 stands for D86, which is the physical
Okay, the
distillation.
D86, yeah.
Yeah, and the group 1 and 2 makes it the AC 8612.
Yes, of course. Of course, so
Yeah,
for
yeah.
group 0, 1 and 2, yes, quindi
Yeah.
esatto,
Zero is not there in the latest version.
Yes. Yeah. Okay.
The same as the AC 8634, which is basically, in between brackets, just a mid-distillate SIMDIS reporting correlated data for group 3 and 4. Jet fuel.
Yes, both reported correlated data.
No, the SIMDIS reports correlated data, and the AC 8612 reports calculated data based
Calculated data on the fugacity field model. Okay.
Yeah.
Okay. Ok, Fabrizio, possiamo concludere?
Sì.
Avevamo...
È stato un evento molto interessante, grazie Teo per una carrellata molto esaustiva sulle metodiche in utilizzo. Possiamo aggiungere, Gianluca, se non sbaglio, a livello di promozione, eventualmente sulla linea della distillazione simulata di PAC, un periodo di scontistica dedicato alla linea, una buona scontistica del quale non ci dedichiamo adesso a dare numeri, ma avrà una validità abbastanza ristretta nel tempo, quindi nel caso vi invitiamo a contattarci per definire un valore di commercializzazione dedicato alla distillazione simulata di vostro interesse. Ma una scontistica è una promozione che potremo applicare a tutto il portfolio della distillazione simulata di PAC, di conseguenza, come dire, dai gruppi 1 e 2 fino alle varie metodiche dedicate al crude oil, quindi nell'intero range di applicazione. Tutte applicazioni sviluppate su gascromatografica 8890 di Agilent.
Va bene, dai, può dire che possiamo chiudere. Ringraziamo di nuovo tutti. Io ringrazio Laura e la Sabrina perché hanno lavorato in backstage per organizzare un po' tutto l'evento. Ringrazio Fabrizio e thank you Theo and Rob for your presentation.
Yeah.
And,
Thanks a lot,
rimaniamo ovviamente a disposizione come sempre per sviluppare applicazioni per qualunque vostra domanda ulteriore. Grazie e buona giornata.
Grazie.
Grazie a tutti.
Ciao.
Thank you.
Thank you.
Ciao.